Okay, so solutions is a unit in chemistry that basically just covers the way things dissolve in water. So if we're looking at this pretend beaker here with a solution in it, the substance that is being dissolved is called the solute. Okay, and that can be a solid, liquid, or a gas. So for example, in the picture, it looks like a solid, so something like salt can dissolve in water. Could also be a liquid. So alcohol is alcohol dissolved in water. And then we can also have gas dissolved in water. So that's like carbon dioxide and soda. And for the purposes of chemistry 1, the solvent is always water. If you go into higher level chemistries, there are other solvents. You can use stuff called hexane, or you can use alcohols to dissolve things or whatever. But usually for the this class, the solvent is going to be water, and the solute is going to be whatever else. So there's two different types of solids that can dissolve in water. We have electrolytes and not electrolytes, and we've had those words before. Okay, an electrolyte is a substance that conducts electricity when it's dissolved in water. And salt, of course, is like the most commonly used example. The reason why is because when the water molecules approach the salt, since water is very polar, the positive and negative part of water attracts the positive and the negative sodium and chlorine. So water approaches the salt molecules and then it takes pieces of it away at a time. So like this right here. Okay, those are negatively charged oxygens surrounding a positively charged sodium. So the sodium leaves the cluster of salt and it goes with the water out into the liquid. And then we also have this section where you can see the positively charged hydrogens being attracted to the negatively charged chlorine. So now that this negative and this positive aren't close to each other anymore, we now have charges floating out in the water, and we've drawn that before, like Na plus 1, Cl minus 1, Na plus 1, Cl minus 1, just showing how it breaks up when it's dissolved. Okay, and those separated charges are the reasons why electrolytes can conduct electricity. There are also substances like sugar that are non-electrolytes. So if we look at this picture right here, okay, obviously they didn't take the time to like write out the whole entire molecule of sugar. But what you can see is maybe there had been a sugar cube down here. Okay, very similar to the salt cube in the other picture. Sugar is polar. So water still likes to take pieces of sugar away with it, but instead of taking like only half of a sugar molecule, it just takes the whole entire thing. So you can see there are positives and negatives. Oxygen is the positive hydrogens are hanging out with the negative oxygen, and then we've got the negative oxygen here hanging out with the positive carbon and hydrogen. So there is some polarity in sugar, which is why water likes it, but that C12H22O11 does not split up. Okay, that molecule stays together and water just takes it away. So this is considered a non-electrolyte because it does dissolve, it does split up into smaller parts. Oops, I missed an L there. It does split up into smaller pieces, but it does not separate into charges or dissociate, so it's considered a non-electrolyte. Okay, so solubility is the ability to dissolve, and there are some factors that can influence how well something dissolves. There is mass. Okay, obviously, if you're trying to get 100,000 kilograms of salt to dissolve in 1 milliliter of water, that's not going to work. It has to be a good ratio of the right amount of water and not too much substance in order for it to dissolve. Okay, what else works is temperature. Okay, so if you look at this graph, we have increasing temperature down here. So most of them are increasing as the temperature goes up. In general, for solids, so if you look at the way the graph is separated, in general, solids dissolve better in warm water. So for example, if we look at this line right here, okay, this represents how KNO3 dissolves in water. At 0 degrees, in 100 grams of water, we can only dissolve about 10 grams of KNO3, but as the water warms up, you can get way more potassium nitrate to dissolve, and then of course it just goes off of this chart infinitely, essentially. The other thing that works is pressure. Okay, if we want, what you might notice on this graph is that gases do not dissolve well in warm water. So these three substances right here, they're dotted lines because they're gases. Gases like cold water. So they all start at a higher point, and then as the water warms up, they start to drift downward. So they're the opposite of solids in that way. The other thing that helps gases dissolve is pressure. Okay, if you're increasing the amount of pressure on the surface of a liquid, you make it really hard for the gas to be able to escape. So you're going to end up having more gas stuck in the water as long as you keep that pressure high. So if you've ever heard like the hiss when you open up, a soda bottle or something, that is because those bottles are pressurized. And when you crack them open, they start to bubble because you've just depressurized them, which means that now the carbon dioxide, it's making it easier for it to escape. And the last thing that helps substances dissolve is size, and we're talking about surface area for this. So if you want a substance to dissolve faster, the smaller the pieces are, the quicker it dissolves. So for example, a giant cube of salt is going to take a long time to dissolve, whereas if you have it broken up into little pieces, the water can flow in and around those pieces much easier, and dissolving only happens from the outside in. So the smaller the pieces, the quicker they're going to dissolve in water. If you're asked questions like the one here, what mass of ammonium chloride dissolves in 100 grams of water at 70 degrees, you really just have to find where the substance and the temperature match up. The 100 grams of water is just referring to this right here, the y-axis. The y-axis, and for some reason the pen's not working. There we go. So the graph is basically saying, just assume that everything on this graph is happening in 100 grams of water. So the way these gram markings stand for how many grams of the substance can fit into that water at these temperatures. So for answering this question, the ammonium chloride line is this one. 70 degrees is right here. So I'm going to say that roughly 60 grams of ammonium chloride can be dissolved in 100 grams of water at 70 degrees. Okay, similar question. What's different here is the amount of water. So now we're looking for sodium nitrate at 10 degrees. So that is NaNO3 right here. Whoop. Okay. 10 degrees is right here. So if this question was exactly the same as the last one, and it was just asking about sodium nitrate at 10 degrees, the answer would be 80. But here's what we have to consider. 50 grams of water is half of what this graph is actually telling you. So this graph is saying, assume you have 100 grams of water. Our question says, now you only have 50. Well, if we only have half as much water, then that means we can only fit half the amount of solute in it. So if it was going to be 80 grams, okay, now we can only do half, so the answer is 40. And we would do the same thing, like if it had said 200 grams of water, that means it's double. So if we have double the amount of water, that means we can have double the amount of solute. So the answer would have been 160. All right, let's see. 50 grams of potassium chloride are dissolved in 100 grams of water. So that means read the graph like normal. 50 degrees. Okay. So every time you read these questions, find the substance and find the temperature. That's the easiest way to start. So potassium chloride is this line. 50 degrees is right here. So these lines represent what we call saturated solutions, which means it's the maximum amount of solute that you can fit in the 100 grams of water at that temperature. And this question is saying that we dissolved 50 grams of potassium chloride. So the issue here is our saturated line is at about 42, and this question says we managed to get 50 to dissolve, which either means we heated the water up really fast and let it cool down too quickly for the substance to be able to fall out or whatever. I don't know. Somehow we got 50 grams to dissolve, even though 43 is supposed to be the max. So if you are dissolving an amount that is above the line, that is considered a super saturated solution. If we were creating a substance, or a mixture that had ended up below the line, so remember saturated is like 42, 43, if the question had said like 35, that would be what we call an unsaturated solution. So since this one was saturated is 42, 43, and this was 50, the answer to this one is supersaturated. Okay, last example question. Let's see, saturated solution of ammonia, which is NH3. 100 grams of water means read the graph like normal, so we don't need to worry about that. 10 degrees. So here's your substance, here's your temperature. We're going to start there, which is right here. How much ammonia will escape as the water is warmed to 50 degrees? So that means we're having a change of temperature. We're starting at 10 and going to 50. So the line, this dotted line that NH3 is on, represents saturation. So if it's saturated at 10 degrees, there's 70 grams in it. Okay, as the water is warmed to 50, it's going down, down, down to here and stops at 30. So that means the maximum amount we can have at 10 degrees is 70 grams. Now we've let that water warm up, which means that we now can only fit 30 grams. So if this question is asking how much escaped from the water, the answer would be 40 grams escaped. Okay, and the word escape implies that because ammonia is a gas, it bubbled out of the solution. Okay, how are solutions different than pure water? That's a good question. Colligative properties are properties that change when a solute is added to water. So the first one that you have to know is vapor pressure, which is the amount of evaporation that happens on the surface of a liquid decreases. So here's your pure water with lots of water vapor on the surface. Okay, as salt is added to the water, you can see less and less salt or water vapor is bouncing there at the top. So as solute is added to water, it evaporates more and more and more slowly. And vapor pressure is directly related to the ability to boil. So boiling happens when vapor pressure is equal to the atmospheric pressure that's pressing down on the liquid. So if you're having less and less vapor pressure, that means it's going to get harder and harder and harder to get to the boiling point, which leads us to the next colligative property, okay, which is called boiling point elevation, or boiling point raises up. Okay, the pink line here represents the normal phase diagram. So let's say this was 100 degrees Celsius. Okay, here's your normal boiling point for water. Okay, if we add solute, you can see the line shifted to the right. So now the boiling point might be 105 instead. And we did a lab like this in class where you made a graph. Everybody had a different amount of salt. Okay, and it wasn't perfect, but in general, okay, it was kind of like going in this direction. So as you added more NaCl, the boiling point got higher and higher and higher. Boiling point was here. So we went from, maybe this was 100 degrees, and it went all the way up to, I think, 105 in one of the classes. And the last colligative property is called freezing point depression or freezing point decrease. So again, maybe here's the normal freezing point at 0 degrees. Okay, you can see that if salt is added, then we're going to go down to like -5. So as solute is added to water, it becomes harder for the water to freeze, which you know because in the winter we add salt to the streets to keep ice from forming, because if the water is salty, then it's going to have to get even colder for it to freeze. So if we're only just below 0 and the water has a lot of salt in it, it's going to stay liquid instead of freezing up.